Hello, everyone. Welcome to Rational Science from Frankfurt, Germany, live. Today we're going to talk about, we're going to not talk about, we're going to have a tour. We're going to have a tour through the particle zoo of quantum mechanics. Now, how's that for a subject? Okay. We're going to do a little revision of what these people have found over at least specifically over the last 100 years. Okay. Okay, so where do we start? Well, we have to start in the 19th century to get a little our bearings, 19th century was a century of waves. Everybody believed in waves. Early on in the century, you had people who started contradicting Newton. He was the Einstein of those days. And so they challenged him. They said, look, we can't explain what we see in the lab with particles. Newton was a particle guy, right? And so you had all these other folks, especially the French, and they started saying, it looks like you're confused, Newton. Looks like light is really mediated by waves of some kind. It's got this wavy, vibrating, oscillating motion in there. And so they believed in waves. And you have people like Thomas Young, who in England proposed the slit experiment. He tried to explain that with waves. And then you had Augustin Fresnel in France. He was able to explain not only the slit experiment, but later on polarization with waves. And so the wave was, introduced and grounded in the minds of the mathematicians. The question that came up in their minds, which probably also happened in the 18th century, before that, was what was it that was waving? And of course, everybody said, well, it's the ether. And the ether was a notion that came from the days of the Greeks. That was this bunch of particles that filled the vacuum, or that was the vacuum, either filled or was the vacuum. Some people equate it with a vacuum. Some people say, no, it just fills the vacuum, like the vacuum's something else, okay? And that's the big problem. People have never been able to define what space is. They don't understand what space is. We cannot relate to what space is because space is nothing, and we're not used to nothing. We're always we deal every day with somethings, not with nothings. And so when people say, look, space is nothing, well, what do you mean by that? Or what does that mean, And so, yeah, they turned space into something. The Greeks did, and everybody to this day thinks that space is something. Quantum mechanics, mathematical physics, completely general relativity, string theory, they all treat space as something. What was that something in the 19th century? That something was the ether, okay? And really nothing's changed. Today we gave different names to the ether, but the ether is still there. The ether is this body of particles. That's what it is. That's what the ether has always meant. People who are outside of that don't understand what the ether is. They've got tiny brains because they cannot relate to what ether is. Ether, bunch of particles. Okay? So that's what happened in the 19th century. What was waving was the ether. Well, towards the end of the century, a couple experiments indicated to the mathematical community that there was no ether. Okay? Whether that was true or not, irrelevant. The point is that people believed it. People stopped believing in the ether as a medium, or they started suspecting, questioning. And what came immediately after that was quantum, exactly at the turn of the century. We have Mr. Planck. He says, light comes in discrete packets. And in Einstein, 1905, he came up and he used that. He quantified that to explain the photoelectric effect, and from then on, we had the particle again. So the turn of the 20th century, from the 19th to the 20th century, was a major revolution because they went back to Newton. They said it's particles. except for one little teeny weeny detail, and that's that the particle was not a particle. The particle was a number, was a value, was an amount, was a quantity. It was no longer a little ball. It was not a corpuscle. It wasn't a speck of dust, a ball. And that's what we have today. We don't have balls. To this day, no balls, okay? It's all numbers. These are mathematicians talking, not physicists, okay? So when you listen to a mathematical physicist, especially a quantum mathematician, quantum physics, or string theory, when they talk about particle, when they use the word particle, they don't mean particle. That's just misleading. That's a euphemism to mislead you, to make you think that we're talking about a little ball, which is what they're going to use to illustrate their physical interpretation. But it bears no relation to what they do in their offices. In their office, they talk about one thing and one thing only, and that's numbers, quantities, values. Okay? So when they accelerate or smash, they're not accelerating or smashing balls. What they're doing, is they're accelerating and smashing number 5s and number 10s. They're smashing a 9 against an 8. Okay? You got to keep that in mind, because that's the problem. The problem is these people are using abstractions, and that's what they say is happening physically in the lab, in the accelerator, at the LHC and so on, SLAC, Fermi Lab, Brookhaven. Okay, so early on, the first 20 years, they tried to figure out, what that invisible world was that they had out there. What was this world of atoms? Okay, because they had already come up to speed on the idea that, that there were atoms out there, that there were particles. That's the way they saw it, flying around. They said, well, air is made out of particles, water is made out of particles, iron is made out of particles, everything is made out of particles, atoms. And they were trying to dig deeper into the atom to find out what the atom looked like, okay? Partly because they wanted to develop technology, okay? That was part of the issue. There was this invisible world. They were trying to pry it open, to peer inside there, okay? And so first we have these two gentlemen, one in 1913, make them a little bigger. Here we go. 1913, Niels Bohr, he came up with this planetary idea, planetary model of the atom, and that was more or less confirmed in the minds of the mathematicians when in 1919, Rutherford does his gold foil experiment and realizes or proposes that the atom is mostly empty space, and it's got some, what he called, positive charge in the center. The positive and negative labels were given by Ben Franklin 100 years earlier. So he comes up with this and he says, okay, we have a proton in the center, that's the positive charge, and we have the electron on the outside. This was the model. And with this model, they lasted for the last 100 years, essentially. This is the model that we have today. This is you might say, well, this is not really the model of quantum mechanics. Well, I don't care what the model of quantum mechanics is, because this is the model they use for everything, to explain everything. That's where the problem is. So if quantum mechanics has a different model, the cloud model, the whatever model out there, the layered model or the orbital model, we don't care, because it has no bearing on what people are taught and on what and how they explain things. When you explain quantum jumping, when you explain electricity, and when you explain ionization, that's the model they use, and that's the only model they can use. So this is the model. Sorry. If you got a different model, draw it. After all, they claim that they've seen these, that they've photographed them, and that they whatever, that they shook hands and interviewed them. Fine. Draw it. I need to see your atom, if it's not this one. Otherwise, this is it. Okay? And so this is the model they used. And of course, they realized there were problems with this model. One of the big ones was that if the electron was just circling around, why didn't it fall towards the nucleus? Good question. First of all, what keeps the electron from flying away? Second, what keeps it from falling in? I mean, is it running on a track? Is it on a roulette kind of track? Why doesn't it fall in or leave spontaneously? And that was the problem with that model. They realized that it was a mathematical model only. They could explain it mathematically. They say, okay, this guy goes around, and this more or less mimics what we saw in the lab. Okay, a solid positive proton center with the electron flying around somewhere. Okay, fine. So this was the notion they had, but they have no way to make sense of it. Okay, and to this day they can't make sense of it. Okay, what happened was that there was a phenomenon going on, and that was beta decay. They were aware of beta decay, that an element could transmute into another simply by having what eventually became, because at the time they had no idea why that happened. Okay, so they were trying to figure out, they were trying to propose theories of what was going inside the atom that would explain this beta decay, this transmutation. Okay. And so Wolfgang Pauli comes up, and he comes up with this model. He says, there's another particle in there somewhere. Okay, and these are his own words here on the right. I have hit upon a desperate remedy to save the exchange theorem of statistics and the law of conservation of energy. What happened was that he had a little debate with Niels Bohr, and Niels Bohr said, this is a statistical fluke, a statistical issue. And that would have given jobs to a lot of statisticians and kept the so-called mathematical physicists out of it. And so Pauli said, no. I can give you a better idea. I'm going to create a new particle, and that's going to set the equation right. Okay. So he said, namely the possibility that there could exist in the nuclei electrically neutral particles that I wish to call neutrons, which have spin half and obey the exclusion principle, which is what he had developed in 1925. By the way, by 1927, they had all these principles that formed the foundations of quantum mechanics. One was the exclusion principle, for which Pauli gets the Nobel Prize eventually. And then there were two other principles, one by Bohr, the complementarity, and the other one by Heisenberg, which was the uncertainty principle, for which he won also the Nobel Prize. Okay, so these foundations were established before any of the particles that we're going to talk about today ever came into existence, before they ever ran any experiments. So they already set the foundations of quantum mechanics, and generation after generation has simply memorized these foundations, these cornerstones, right? Okay, anyways, he said that I wish to call neutrons. Okay, so he's the guy who invented this word neutron. And we'll see what happens with that word. Which have spin half and obey the exclusion principle, and which further differ from light quanta in that they do not travel with the velocity of light. Okay? The mass of the neutrons should be of the same order of magnitude as the electron mass, and in any event no larger than 0.01 proton masses. In other words, it was very low mass, the particle he was suggesting, traveled almost at the speed of light, okay? And the word neutron meant that it had no charge. That was important also. It had to have no charge because it would have upset the balance between electrons and protons. The continuous beta spectrum would then become understandable by the assumption that in beta decay, a neutron is emitted in addition to the electron, such that the sum of the energies of the neutron and the electron is constant. Okay, so this was an accounting procedure that Pauli suggested or invented, right? He had to win that debate with Bohr. That was essentially what it was about. Okay. One guy said, look, it's just an accounting procedure. We've got a little, fluke in the in the statistics. It was a statistical fluke. Bohr said that, and then Pauli, on the other hand, he said, no, 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 there's a particle in there. And so they invented the particle to make the equation come out right. Okay, keep that in mind. Okay, that's how it works here. Okay, you first do the equation, you see something's missing in here. Okay, put a particle in there. That's how it works. And then they tell the particle accelerator people, the particle mathematicians, the guy who work at the lab, say, go find it. You're looking for a particle that has no charge, that has so much mass, travels at the speed of light, has so much spin, etc., etc., etc. And so that's what they look for at the lab. They go to a lab and they say, okay, we're looking for this monster. It has all these properties. That's what the guys, the theoreticians upstairs, that's what they want us to look for. And that's what they look for. And then when they find it, the theoretician and the experimentalist, they both get a Nobel. That's how it works. Who gives them the Nobel? Their buddies. Because they were able to convince them. That's how it works. That's the system. Okay? Okay, so here we have Mr. Chadwick. He comes around the same time. He published his paper in 1932, but he was already working on it, for the last couple of years. Okay, and so Chadwick says, look, I found out something very strange here. It turns out that helium is element number 2. And so if hydrogen is element number 1 and helium is element number 2 and has 2 charges compared to 1 charge for the hydrogen atom, well, how do you explain that? Well, you just have 2 protons in there and 2 electrons. We're done. But that wasn't the case. When he ran his experiment, he realized that helium weighed a little more than just 2 hydrogen atoms. In fact, it weighed almost like 4 hydrogen atoms. And so he said, well, how do we explain this? And that's how the neutron came to be. The neutron had to have no charge, again, because it would upset the balance between electrons and protons on the one hand, but on the other hand, it had to have mass. In fact, the mass approximately of the proton, in fact, a little more than the proton. And that's the guy that Chadwick discovered or invented. That's what he proposed, and he was given a Nobel for that. And so if that was the neutron, because that was inside the atom, then what was this little particle that Pauli was talking about? Did that exist? How can we make sense of that? And that's when Fermi, Enrico Fermi, an Italian guy who eventually worked on the bomb in the United States, he talked to Pauli, and they had a chat. He liked the idea that Pauli proposed, and he went out there and did all the math for it. He tried to figure out if that particle could exist. Was it even in the works? Was it a possibility? Okay, and so Fermi comes around 1934. He publishes his paper. Okay, and he says, this is what happens. What happens is we're going to name it a neutrino. Okay, so they gave it a new name instead of the neutron. Chadwick had stolen that one. Okay, so they say, okay, the neutrino comes out together with the electron, and that's where the transmutation occurs. A proton is because you have, for example, this is just an example. Carbon-14 turns into nitrogen-14. And so the issue is you go from 6 protons and 8 neutrons, and you go to 7 protons, 7 neutrons. And so a proton changed into a neutron. And then you have also in other cases where neutrons turn into protons. Okay, so that's the exchange that you had to explain that transmutation. How does a proton gain or lose charge and become a neutron? How does a neutron, gain charge and become a proton? That was the issue. And the weights, the masses had to remain the same. And then eventually also we had this issue of spin, which is going to come some years later. Okay, so he gives an explanation. Actually, this is a theory. This is an explanation of what's happening in there based on particles. If particles exist, this is what they're talking about. But the issue here is that, again, these are not particles. Because when a mathematician talks, a quantum mathematician talks, he doesn't talk about particle, he talks about mass. And he talks about charge. That's what he talks about. And so when you say, well, particle, are you talking about a speck of dust, a little ball? No, it's we're talking about mass. But I thought physical objects were the ones who had mass. Okay, so this is where the problem is. These people are talking about mass and charge. They're talking about their equations, their numbers, their calculations, their, what they do in the office. And you want to know about physics. You want to know what's physically going on in there. So they illustrate it like this, but that's not what they really mean. They're in a different world altogether. They're just talking about numbers and quantities. Okay, so it's important to keep that in mind. Otherwise, you lose track of what quantum really is about. Quantum is not a particle theory. Quantum is a mathematical description only. Okay, they just try to describe what's happening in the invisible world out there with equations and by creating all these masses and charges and spins. They put them into what they call a particle, which is not a particle, but they have to illustrate something for you to understand them, so they put a ball. And they say, yeah, that little ball, that's the electron ball. And it's got so much charge, so much mass, so much spin. That's how they do it. But when you say, well, what is the electron? Can you draw it for me? Well, we don't know what the electron is, and that's not important for us. For our world, the world of math, quantum math, we're just concerned about these quantities because that's what we can put in an equation. We can't put the word ball in an equation. We can't say, well, ball plus ball equals what? Square or a cube? They can't do that. They can't put an elephant and, I don't know, a rhinoceros in an equation. They have to put the masses and how they're spinning and if they have charge or neutral, that sort of thing. That's what they deal with. So until you get a handle on that, you really have not grasped what quantum mechanics is about. Okay, you have to understand the world of mathematicians. Okay, a year later after Fermi came up with his idea, Yukawa proposes something else. He's a Japanese fellow. I talked about him the other day. And he says the interaction energy calculated on such assumption is much too small to account for the binding energies of neutrons and protons in the nucleus. He was trying to solve the issue of what's happening inside the nucleus. Why doesn't the proton expel another proton? That was the issue that was in their hands, that they were trying to solve. And so he invents a new particle, the meson. Okay, meson. The transition of a heavy particle from neutron state to proton state is not always accompanied by the emission of light. Okay, light particles. Neutrino and an electron, but energy liberated by the transition is taken up sometimes by another heavy particle, which in turn will be transformed from proton state into neutron state. And that's when he proposed the meson. Okay, I like to call them mesons. Used to live in Mesa, Arizona, so I call them mesons. Okay. They were, again, trying to find all these particles that were part of the nucleus. They were going deeper than what Rutherford had gone in 1919. He just did a gold foil, relatively simple, crude experiment compared to what came later. What came later, they started smashing particles, breaking them apart, and say, what kind of debris do we get out of all this? Okay. And so one of the guys that did that, who ran these, was Carl Anderson, and he came up with what I call the suppositron. He called it the positron. I call it suppositron because he supposed that he was dealing with particles. And essentially, he saw a mark on a plate, lead plate, and so he says, that was made by the positron. And he said, well, how do you know that? Well, see, they had these magnets on the sides, and if the particle went right, which is what it was supposed to, in the direction in which it was supposed to go, because you had the magnets put in that direction, then it was an electron. They said, well, this would have been an electron. It turns out that the particle went in the other direction against the magnets, and they say, oh no, this is a positive particle. And because of the mass and all and the speed and all of these other issues that they looked at, they said, oh, this is not a proton, this is not a neutron, this is a positive electron, a positron. Okay, so he got a Nobel for that. Okay, Nobel smiled at him. Okay, so and then same year he also discovers the muon. Okay, and with the mu meson that they thought was what Yukawa was searching for. Okay, which the particle that Yukawa had identified. And it turns out that this was too heavy to be the particle that Yukawa was thinking of. So they said, no, this is a different particle. And so this was a mu meson, and they call it the muon. Okay, and from that point on, they said, okay, where did this guy come from? And that one also came from the sky. One of those particles, cosmic particles, okay? Okay, so they were starting to discover all these particles. And just when they were almost there, World War II breaks out, okay? So once World War II breaks out, all that effort in civilian physics was diverted towards military purposes, and especially, the development of the bomb. Some of these physicists were put into rocketry, and so on, and developing better airplanes and so on, and others were put into the nuclear program, to secret in different countries. The British did it, the Germans did it, the Americans did it. And so they went out there and they tried to figure out, if they could, because they had proposed that you could produce a big bang from atoms, especially from uranium. And when the politicians caught a whiff of that, especially the military, they said, "Oh, hold it, let's see, maybe it's worth investigating." And a lot of them were skeptic. They said, "Well, it's not going to happen." So they took all these physicists, so-called physicists, and they put them into work, as theoreticians. For example, the Manhattan Project that developed the bomb in the United States. There was another one in Britain, and Germans were working on that. So they were all working in secret on these projects, and for that they needed all these mathematical physicists who were working on the atom. Okay, so there was this interregnum, this period in which no more particles essentially were discovered. In fact, for 3 years, I think the Nobels were not given out, were not handed out during the war. And after the war, well, everybody more or less went to normal, and they went looking for particles. Okay, and in 1952, they developed the bubble chamber. They had until then they were using a cloud chamber, and I'll go over that in another day. And now they invented the hydrogen bubble chamber. And what that allowed them to do was to look for traces of particles in a little more detail. Okay? And yeah, suddenly you entered this particle zoo. They discovered particles everywhere during that decade, the 50s. Everybody was discovering particles. They say, "Oh, I found a new particle. Give me my Nobel." Everyone was shouting for their Nobels. Give me my Nobel. I found a particle. And I forgot this fellow. And this Chadwick. Okay, just showed him a minute ago. These two fellows. They made a comment that puts it in the proper light. Oppenheimer said the Nobel Prize should go to the physicist who has not discovered a new particle this year. And Fermi, he said, if I could remember the names of all these particles, I would have been a botanist. Yeah, I mean, they were discovering particles left and right. And so this created somewhat of a quandary, because people were wondering, do these particles really exist? Does the atom contain all these particles? Where are they coming from? And they had in the back of their minds what Dirac had said in the 30s also. Paul Dirac, he came up with this sea of virtual particles, negative and positive particles that form space. Again, the ether. Particles forming space, the background particles, And so a lot of people were starting to come up with this idea that some of these particles were coming in from the void, from this unseen space. They had to borrow it from somewhere for the equation, not because the particle was there out, in real life, that it existed out there, but they had to say, well, how do we get this equation right? Well, put this particle. Okay, so they put the particle with all these parameters. And you say, okay, I got the particle. Now the equation checks out, but where did this particle come from? And so they had to make, that reinforced in them that the vacuum was made of particles, because they had no other place from which to draw these particles. The atom was complete pretty much in many ways, right? And so they said, where are these particles coming from? And especially when they saw these cosmic particles like muons and pions, they say, all this stuff is in the vacuum. Vacuum is made of these particles, or these particles fill the vacuum. They had to figure out, a way of explaining that. What they said, well, you got a positive particle and negative particle. They come together and they form a no particle. And that's essentially what Dirac had said. He had the particle and antiparticles. And so they combine to form nothing. Or like I like to say, a black ball with a white ball forms a no ball. And then they separate, the no balls separate into black and white balls. That's their world. Because they have no other way of explaining this in terms that you would understand. Okay? So when they do their calculations, they're safe. They're in their world. Nobody touches them. But when they have to go out there and explain to the layman, what are we paying you all these tax dollars for, maintaining your projects? Well, let me show you. This is a white ball. This is a black ball. When they come together, they form no ball. And people look at that and say, are you kidding me? They say, hey, we're the mathematicians. Do you know more than we do? And that's what it's all about. It's all about these people just telling the crowd, hey, we know, we got the PhDs, we've done the experiments in the lab, we have the equations. They could have told them anything. They could have said it's angels or spirits. It would have been no different. In fact, it is no different. There is a small difference. Angels you can imagine. Spirits you can imagine. Casper the Friendly Ghost, you can imagine that. These guys are talking about quantities that are flying around. That you cannot imagine. So, yeah, it is unimaginable, meaning it's irrational. That's what quantum is. Okay, so what happened after that, we have this, just the particles galore. Okay, now we get into the particle zoo. So get ready for the tour now, okay? We start the tour. Here it is, okay? These are the milestones that we had in the last 75 years since World War II. First, they detected the mu meson, okay? The muon. In fact, it had already been detected earlier, by Carl Anderson, the cosmic ones. This one was from inside the atom. In 1949, they predicted the repulsive forces between two nucleons become attractive in the nucleon anti-nucleon system, forming the pi mesons. Okay, well, what it is that you gotta figure out how attractive, how to produce attraction in quantum mechanics, and they never figured that out. They were never able to figure out how to produce attraction. And so the way they do it is they do it in strange ways. They simply change the charge. For example, here's an example, okay? If I can find it. Here it is. Here's an example, okay? What you see is two up quarks and down quarks at the top. And what we're going to do is we're going to change these down and up quarks to the other, okay? And essentially what they're saying is this is how a proton turns into a neutron, neutron into a proton. In other words, how it gains charge, how it loses charge. Well, great. Just tell me how atom 1 attracts atom 2. That's what I need to know. I need to understand attraction. I need to understand pull. The only force that quantum mechanics will never be able to answer. They can answer push, particle against particle, but you cannot answer pull, attraction. Okay, action at a distance, attraction. How do you pull something from a distance if you're going to mediate it with particles? So what they do is they say, well, very simple. See, you have these gluons, the little two balls that are flying around, those pairs of balls. What they do is they change an up quark into a down quark or vice versa. Okay? So by doing so, you change the charge. And as we all know, positive attracts negative and negative attracts positive. And positive rejects positive and negative rejects negative. Yeah, but you haven't explained the mechanism. All you're giving me are descriptions. All you're telling me is a positive turns into a negative. What does that mean? What does that mean in physical terms? Okay, so this is the underlying problem, okay? That these folks are simply telling you that positive turns into negative, and that's how they produce attraction. Because we know that the positive side of a magnet attracts the negative side of a magnet. That's all they can say, okay? So it's not a mechanism. They haven't explained the mechanism. Anyways, 1952, they invent the hydrogen bubble chamber. 55, they discovered the anti-proton. See, now we have these antiparticles that they had to discover, okay? And just a short time later, a few months later, they detected the anti-neutron. So now we have these antiparticles. So how does an antiparticle differ from a particle? I mean, what's different about them? The structure? I mean, structurally, what's different? And all they can tell you is that one has that when one combines with the other, they annihilate. What? Virtual particles. Where do they go? They go to form the vacuum. What is the vacuum? Made of particles, which are annihilated. So they have these dualities where you don't know if the vacuum is made of particles or made of nothing. Because if they annihilate, what did they annihilate into? Well, they annihilated into nothing, and nothing is made of two particles, or one particle, or whatever. You know, I mean, it's made of particles. So we don't know what annihilation means, because if two particles, an antiparticle and a particle, come together, they annihilate. But what does that mean? What do they turn into? They turn into a particle, into nothing. If they turn into nothing, what is nothing? Okay? So again, they use this and they leave it open-ended so that nobody asks these questions. Okay? Okay, then they also detected the neutrinos in 1956, okay, for the first time. And I discussed that the other day, Cowan-Rhine's experiment. They received, well, one of them receives the prize 40 years later. The other one died, so he didn't receive the prize. In 1960, they were also trying to unify the electromagnetic forces with the weak forces, okay, the photon with the W's and Z's. They were working on that problem, okay, and I showed that the other day. They detected cosmic neutrinos, okay, these, again, flying from stars, and they say that these neutrinos were actually created immediately after the Big Bang. There's gazillions of them just flying around, and so part of that cosmic background radiation includes neutrinos. What happened also in the 60s, mathematical formulation of spontaneous broken symmetry in quarks. 62, discovery of the muon neutrino. They proved that there were at least two neutrinos, so now there was a search for these extra neutrinos, especially the search for naming them. Strangeness and quarks were invented in 64. Also in that year, discovery that matter and antimatter symmetry is violated when the neutral K mesons decays. Great. Okay, fine. So you can see what these people are doing, what their research is into. They're just looking at all these mesons and pions and subatomic particles, working with their energies, which they turn into mass, and their charge and with their spin. That's essentially what they do. That's the job of a mathematical physicist, both theoretician as well as the lab guy. And then in 68, they finally had evidence that quarks really do make up protons and neutrons. Until then, it was just theoretical. Okay, you can see starting in 70, I started putting the dates. This is important for you to keep an eye on now. They started putting the dates. I put the dates when they received the Nobel. The dates on the left show when the guy discovered whatever they discovered, And on the right, you'll see, right at the end in parentheses, you'll see the date when they received the Nobel Prize for their discovery. And you can see the quark inelastic scattering, virtual photons can knock out a quark out of a hadron, okay? That was discovered in 1970. They didn't receive the prize until 1990 for that discovery. 73 predicted bottom and top quarks. They didn't receive the Nobel until 2008, quite a few years later. Asymptotic freedom, very important topic because, again, it's they exchange the gluons, and this is what keeps the quarks bound to each other. In other words, what these people say is that a quark attracts another quark because they exchange gluons. Well, what do you mean by that? How can you exchange little particles of force, whatever that means, and produce attraction? How do you pull by throwing particles? A quark throws a particle at another quark, a down quark at an up quark, for example. Okay, so you threw a gluon at it. How do you produce pull with that, with pitching a ball to the batter? Does he come to the mound? I mean, what is this? What are they talking about? What's the mechanism? Okay, and so asymptotic freedom really is nonsense, because they say that all they're saying is the farther something, if you have a lot of energy, then the effect it has on a quark is less. That the quark is stronger, like the attraction force, only when it's inside the nucleus, and there you have little energy. But if you try to smash it and get lots of energy, well, the quark loses its strength. That's all that asymptotic freedom means. And so these are the terms that they've invented. And so, it loses most of the crowd out there. People look at these terms, they don't even know what they mean anymore and what they're referring to. Okay, so again, it's become an esoteric type of discipline, quantum mechanics. It's for a group of people who understand that language, and they only run into trouble when they have to explain it to the layman, because layman will not want to hear all these terms. They just say, give me the bottom line. Tell me what's happening with little balls or with whatever. Just show me a movie of it. And that's when they have to turn their quantities into little balls. Okay? So again, quantum mechanics is not a ball theory. It's a mathematical description. Okay, the charm quark, fourth type of quark. They had to invent another one. They had 3 quarks inside the atom. They had to invent the fourth one in there. Okay, in 1974, electroweak interaction, mathematically fine-tuned by a group of people who received they did that in 74. They received their prize in 99. They discovered the tau neutrino in 95, the cosmic neutrino. They realized it was created by the sun. Okay, so these were cosmic neutrinos. And again, they discovered that in 80 and received it in 2002. Then they finally detected the W and Z bosons, okay, 1984. They received the prize 1 year later. That was quick. And then the last, keep in mind, this is the last one, the last discovery, okay? Neutrinos have mass in 2015. They discovered it in 1998. They received the prize in 2015. For the last 20 years, they have not discovered anything inside the atom, okay? Now, they discovered the Higgs, but the Higgs is a particle related to mass. It's not, it's like more related to gravity, which is like an outside force. Yeah, they claim it's inside the atom, and they can't find it, and it's like they've given up hope on that. Okay, gravitons, as far as I know, nobody's really researching that in any depth. They're working on something else, which I'll go over in a minute. But the peering into the atom stopped in the year 2000, 1998, whatever, turn of the century. So for 20 years, they have not been looking inside really the atom. The Nobel Prizes they're giving now are for anything in the last couple decades of the 20th century. Okay, 21st century, nothing new inside the atom. Essentially, we bring Niels Bohr back. It's a complete theory. Quantum mechanics is complete, you could say, right? And that's it. That's it for quantum mechanics. So what are the new generations going to be working on? You got the Z generation now, the last generation, as I call it. And what are these people going to be working on? They're going to go to the accelerators. And what's there to do over there? What are they going to be doing? Smashing atoms so that they can see inside the atom? And you say, well, we've got so much energy to produce these collisions. Now you need to have higher energies to break whatever's in there even further. And so they build these bigger colliders now. They're working on all these colliders, making them bigger so that they can be accelerated. The particles can be accelerated with more energy, so they can be smashed with more energy to see if they get the little pieces out of there, okay? And they're just going to be naming those. They're just going to give new names to these new particles. What's all that for? What is all this work about? This transgenerational, 70-year work all about? Is it just smashing particles, giving names? I mean, assuming that's what they're doing, assuming there are particles, right? Because we have a totally different model for the atom. But assuming there are particles. Okay, so you smashed it. You came up with a quark here, a neutrino over there, and then you got the gluon over here. Okay, fine. You got all these particles. And what is this for? What is the purpose of all this? It's just giving them Greek letter names? So all these people just have jobs doing equations. That's all they do. And now they ran out of equations because it's like, we're finished. What more are you going to find in the atom? So they created a new branch of science, not of science, but of quantum mechanics. And it's a branch that sticks its arm all the way from general relativity. And that's this one. It's the dark matter that forms the outside of galaxies. And here you can see the summary, essentially. All these quantum particles, or quantum in general, that deals with the matter that we're familiar with, atoms, molecules, everything we see every day, that's only 4% of the matter in the universe. And they have all these descriptions. They don't understand any of it, again, because they're not using objects. They're using concepts. They're using amounts. That's the first issue. The second issue is that even if these were particles, the explanation is irrational, because you cannot explain how, first of all, why the electron doesn't fly spontaneously out of the atom, or why it doesn't fall into the nucleus. You cannot explain that, okay? And physically. You can explain it with math, yeah, you put a negative sign, you get it done. But you cannot explain it physically. You cannot show that on the board. You cannot go to the lab and simulate it with balls, with particles or whatever. You cannot simulate it mentally, let alone in the lab. So we don't have an explanation, even if there were particles, okay? But that's only 4% of the universe. Matter is only 4% according to them, okay? And they say 21% is dark matter. What is dark matter? Well, you have this galaxy rotation problem that you see there, okay? And the galaxy rotation problem is that, a galaxy rotates. First of all, the stars don't fly out. If this is a carousel, why does that star on the outside stay faithful to the center of the galaxy? Why doesn't it fly out? And then the other issue is that they discovered by studying stars going around galaxies that these stars travel as fast or faster than the ones on the inside track. And that's like if Pluto were going faster than Mercury around the sun. How can you explain that? We think that Mercury, because it's on the inside track, goes much faster than Pluto. That's not the case with the stars. The stars, it's the other way around. It's the stars on the outside that go faster. So you say, how can that possibly be? And so they said, we can fix this. And they sprinkled mass, kilograms, out there on the outside, and that's called dark matter. That's what dark matter is about. Okay, so they have that, and so with that they explained in their minds, right, with this ad hoc stuff, they sprinkled matter there, mass, not matter, they sprinkle mass, but they call it dark, not dark mass, they call it dark matter, okay, to show you that they're doing physics, they're still doing physics. Okay, so they have this dark matter out there, and now they can simulate why the galaxy rotates the way it does, okay, and why the stars don't fly out. Fine. But what is this dark matter? Is this just a computer-generated simulation? Is this just an equation? And so they said, hey, you guys at CERN, at SLAC, at LHC, and SLAC and Fermi Lab, why don't you guys look for this dark matter particle, the particles that make up dark matter? Okay, what are we looking for? Well, it's ultra heavy and invisible. Invisible, intangible, apparently, but it's ultra heavy. And so look for it. Okay, so now these colliders are trying to find this dark matter to help the people in general relativity out. It gives both fields of mathematical physics something to do. These guys are doing the calculations, the equations for dark matter, which is already done and it's finished. And these other fellows are going out there and saying, okay, look for it. And so they're saying, okay, let's prepare the collider to see if we can smash particles at such energies, at such force, right, that what comes out of there is a bit of dark matter. And we see it as a trace in some emulsion that they've got in there. We'll see a trace through the hydrogen gas, and that trace has to have these characteristics. If it meets those characteristics, we have found dark matter, give me my Nobel. That's the way it works. That's what they're into, okay? And then we have the rest of the ignorance, because we don't know what dark matter is, so they're looking for that. They don't know really what the 4% is, so I'm being kind. There's 100% ignorance, but we'll live with 96. That's close enough. You can round it off if you want. Then you have 75% dark energy. And you say, what the hell is dark energy? And dark energy is, you have this Big Bang that they claim happened, the origin of matter, 14 billion years or so ago. So there was this explosion, which is not an explosion according to some. They don't like to use the word explosion. Okay, so there's this explosion, as I like to say, ground zero. And all the matter was created in this process, and eventually, and it evolved, and it turned into eventually stars and galaxies and etc. Okay, and in the 1929, I think it is 1930, they finally came to the notion that galaxies are flying apart. But it's not just that they're flying apart. They eventually figured out or discovered or measured that they're flying apart at an ever faster rate. Why? Because the galaxies and stars which are farther away from us are flying away faster away from us than the stars that are closer to us. So if you look at the movie in your mind, okay, the stars and galaxies closer to us are going at 60 miles per hour, okay? And the others are going at 120 miles per hour. And the others are going at 500 miles per hour. So the farther out you go, the faster they go. So the universe is exploding in front of our very eyes. That's the notion they have. And you say, well, what's the problem with that? Well, the problem with that is that you got gravity. They don't know what gravity is. Maybe it's gravitons, maybe it's warp space. Who knows what gravity is, right? And so gravity is supposed to pull all these stars, all this matter, all this 4% matter back together. We should have this oscillating universe, which was one of the proposals originally, right? That the universe explodes and comes back and explodes and comes back. So that was the notion of the oscillating universe. Well, they debunked that. They said, no, it's not going to happen. This thing is going to go out and just fizzle into nothingness. The universe is just going to explode and turn, eventually just wither away. And so you say, what's the issue? The issue is that gravity should be pulling all this stuff back together. What's pushing everything else outwards? That's your dark energy. That's why they had to create dark energy. They created this monster, this invisible ghost that pushes somehow, because energy, is material, it pushes things, right? So energy is pushing all these galaxies outwards, and it's overriding the gravitational attraction. Okay, so that's why they had to create dark energy. Of course, then you have some exceptions which they turn a blind eye to, like our biggest neighbor here, the Andromeda galaxy, which is coming towards us. You say, well, how come that one's blue shifted and coming towards us? That's a fluke. They say, well, somehow gravity is overcoming in that case, right? In other cases that some of the local group, they're coming towards us. Well, in that case, gravity is overriding the electromagnetic or this dark energy repulsion. And that's where we are today. So where are the next Nobels going to come from? Well, they're going to come from dark matter, for one. Maybe string theory, because string theory still is dealing with the graviton and with black holes. So it's possible that there's going to be a Nobel for the string theorists. On the one hand, one of the problems, the strategic problem the string theorists have is that the Nobels are controlled by the quantum guys. See, when you get a Nobel, you get to vote for the next Nobel guy. And so these guys control the Nobel medals. And they say, okay, who do we give it to next? Well, let's give it to one of our guys, one of our quantum guys. And right now they're giving it to their peers. And these guys, the string theorists, they're on the other side of campus. They don't talk to each other, and they say, well, one day you got to give it to us. See, we've done all this math showing that, what happens to a graviton when it falls into a black hole, and black holes are proven. Gravitons are not proven, but, we know what a graviton is. It's a vibration of a little line, right? And so, you got to give us a Nobel too. And so, and because the new generations, the Z generation, the last generation, has nothing else to work on in quantum mechanics, a lot of them are moving into string theory. They say, well, if I'm going to do math, I'm going to do string math. There's no more math left in quantum. And so a lot of people are choosing that they're going into so-called mathematical physics. They're going into string theory. And so eventually you're going to have such a big group out there that you're not going to be able to deny them a medal. You're going to have to recognize them and say, okay, let's give them a medal. And once they start getting medals, they start voting for their own people, and you'll get more and more string theory medals. Until the quantum guys are able to make an atom smasher big enough to produce dark matter. Hopefully they don't produce dark energy, because then, I don't know, then we're all crazy. Okay, so that's a wrap. That's the particle zoo. That's more or less what's happening out there, and that's also what the future looks like as far as all these people are concerned. There's nothing more to discover in mathematical physics. There never was, really. Okay, so let's move on to some of the questions and comments. And I'm going to start with the homework that I had the other day. This was the homework I gave out. Anyone who still wants to do it. We have an astronaut. It's the same astronaut. Okay, he's at two different levels with respect to the Earth. He's standing on a scale in both cases. Same scale, by the way, okay. Does he weigh more, or does he not, or does he weigh differently? That's a better way of putting it. Does he weigh differently at one altitude than he does at another altitude? That's the question, okay? And so here are the questions that you're supposed to answer if you want to tackle the question, okay? The first one, does the astronaut have different weight at different location? If so, which astronaut weighs more? The one on the top or the one on the bottom? Again, it's the same astronaut, okay? Same amount of atoms in him, okay? But the key issue is number 3, why does the astronaut weigh more or the same? Okay, and we need a cause, a mechanism. No numbers, please, no descriptions, and we will call an idiot anyone who says, oh, because of distance. Yeah, we know that. And because of the acceleration of gravity. No, those are not answers. Those are descriptions. We want an explanation of why, what causes, what is the physical cause for an astronaut to weigh more or weigh less, if that's what you believe. Maybe you believe that he weighs the same. Okay, maybe you're a flat earther or whatever. Okay, one fella, I don't know if he attempted to answer this or what, but I'll just put his comment here. Okay, and he says, mass material is the inverse of porosity. Yeah, derivatives from periodic table of elements from which there is a plethora of combinations. Yeah, that's not a definition. That's we don't know what mass is. We don't have a definition of the word mass. And so, until you define the word mass in such a way that, is it quantity of matter or not? That's one issue. You got to say yes or no to that question first. And then you have to say, what's the difference between mass and weight? And specifically, what are you going to put in Newton's equation, or for that matter, Einstein's equation for mass in there? Are you going to put acceleration? Are you going to say that that the more a particle accelerates, the more mass it has, like they say in special relativity and in quantum mechanics? Okay, so this is the issue. Is mass different than weight? Because mathematical physics defines mass as quantity of matter, and then they never use that definition. What they use is always acceleration. They say the more you accelerate a particle, for example, the closer it reaches the speed of light, the more mass it has. And so the question is, did it gain more quantity of matter, or are we talking about something else? Are we talking about weight, the pressure on the scale? Is that what we're talking about? Because that's weight. And so again, there is no difference between mass and weight, and no one on planet Earth uses mass. In other words, quantity of matter. Nobody counts atoms. Everybody uses weight. And that's what they put for mass in Newton's equation and in Einstein's equation. They put weight. Nobody deals with mass at all. Okay, so that's the first thing you got to be clear about. So, just tell me why one astronaut weighs more than the other or not. And then, the cause. Tell me the cause, the physical cause, okay? I think the same fellow said something like this. He said, density is arrived at by dividing mass, weight by volume. The thing I can agree with him, well, I agree with both, but specifically I agree with the fact that he insinuates that mass and weight are the same, and yes, he's right. Mass is equal to weight. There is no difference. That's why he put that in parentheses. And here's another one along the same lines. So if we put an astronaut in a large spinning cylinder in space, we can artificially replicate his weight. True. In fact, I showed that some videos in the past. At the appropriate speed, we can put him on a set of scales and he will weigh the same as on Earth. Yeah, we can produce artificial gravity. There was, for those of you who are in the know, Stanford Torus. It looks more or less like this. It was designed by a joint project between Stanford and NASA. And they said, 10,000 people could live in this torus that's spinning in outer space. And by spinning, it would recreate the 9.8 meters per second square that we have here on Earth as far as gravity is concerned. Now, the question is whether that gravity is the same as Newton's gravity. The gravitational gravity, because gravitational gravity is different than force equals mass times acceleration, in a sense that how should I explain this? We have what is known as the principle of equivalence, and essentially states that force equals mass times acceleration. That equation is equal to force equals gravitational constant g mass divided by distance squared, which is Newton's gravitational equation. They say these two are equal. Why? What's the cause? Under the rope model, it's very simple. I've illustrated that in the past. For any given hydrogen atom, let's assume that's the unit of mass, okay? Put it anywhere out there in space. the number of ropes connected from that single hydrogen atom to every atom on Earth is a given quantity. Let's call it a billion. Okay, so there's a billion ropes connected at that distance. Okay, to the Earth. There's the number of ropes is always the same, but what happens is the number of independent ropes, the ones that are not on the same axis, changes with the distance of that atom with respect to the Earth. So what happens if you just take a snapshot of that atom with all the ropes connected to every atom on Earth at a given distance? For that distance, force in the second Newton's second law of force equals mass times acceleration is equal to the gravitational equation. Why? Because the number of ropes, whether that atom is leaving the Earth or coming towards Earth, at that location, the number of ropes is the same for both equations. That's why the principle of equivalence that's the cause, that's the mechanism that underlines the principle of equivalence. See, Einstein just stated it as a principle. He said, well, I don't see any difference. Yeah, he didn't see any difference because he was missing the ropes. With the ropes, you can explain, now you have a cause. Okay? The number of ropes at a given distance for one atom is the same whether the atom is leaving or coming. Leaving, force equals mass times acceleration. Coming is a gravitational equation. I don't know. I hope you got that. I've got it illustrated. A picture's worth 1,000 words, but I'll just do that another day, maybe next time. Okay, so here's another issue a fellow raised. In fact, two of them. One says, square is in a standalone object. And another fellow says, in fact, fellow I know, geometry is conceptual. Square is a concept. Oh! No, square is not a concept. It describes a relation between objects. Let's find out. Let's find out if any of these two fellows is correct or rational. Okay, so here, let's put it up there. Tell me if that, first of all, if that's not a standalone object. Looks to me like a standalone object. Now, to some degree, he is right. I keep saying the following. I want you to listen to this, okay? If you take a cube, and I'm talking about an ideal cube, in other words, an inexistent cube, because we're talking about perfect geometry, right? Ideal geometry. If you take a cube, a square is the side of a cube. That's it, period. We're done, okay? It could also be the side or one of the ends of an elongated rectangular cube of some kind, but essentially it's a side of a solid. That's what I'm saying. In that sense, he's right in that it's not a standalone object. But here I can present it as a standalone object. All I'm presenting is the square. You don't know if there's a cube behind it. So that is a square. That's what we call a square, and it is a standalone object because I don't need any other object in that frame to relate it to. Okay, I just relate it to the backdrop, that black stuff, which we call space, which is a synonym of nothing, okay, and that forms the backdrop, the background to this square. So yeah, there you have it. I don't need any other object in there for you to understand the word square. That's what I mean by a standalone object. And then there's no relation there in the second fellow there. Square is a concept? No. Concept is a word that invokes two objects. And here you don't see a second object. So there is no relation between objects there, okay? I can make, if God only made one square in the universe, and he has the ability to do that because he's magical, we have a square and we don't have any other object in the universe. We have that sheet, that thin, ultra thin sheet in space, okay? So God made a square, that's all he made. We don't need any other object to understand the word square. That's the point, okay? So, no go there. Here's another comment. See, a lot of people asking questions about the word object. Yeah, the word object destroys all religion. I'm very much aware of that. Destroys all religions. Once you define the word object, everybody who's got a religion is going to suffer. They're going to say, oh no, but hold it, you're raping my virgin here. Yeah, I know. I'm sorry, your icons are dying here. Okay? If it's the only object, there is no background, it doesn't exist. Too many things put into one sentence. He raised too many issues in one, okay? Space is nothing. It can't serve as your background. Well, I don't know. Here we have it as a background. I mean, where was it? Here? There it is. That black stuff is called space. It serves as a background, serves as the background to the moon. It serves as the background to the sun. So yeah, space is what serves as a background to all objects. So I don't know what else you suggest serves as a background. Okay, but then there's the issue of concept. Okay, here it is, and these are the foundations of physics. Okay, he says if it's the only object there is no background, it doesn't exist. Okay, and space is nothing, yeah, but you got to say what nothing is. You got to define the word nothing. Okay, and so we do that in rational science. We have to define what something is when nothing is. And they're antonyms. That way we can use them consistently. Something is that which has shape, and nothing is that which doesn't have shape. We're done. And something is what's on the lower left there, and nothing is what's on the lower right, whatever you see there. Okay, if you don't see nothing, well, that's what it is. Okay, so, and then there was another topic there. Let me put this up here. There's your background. How do you like that? That's space. Okay, nothing. Some paint it white. I like to paint it black most of the time, but sometimes I paint it white. Okay, yeah, space is the background to all objects, to the moon, to the sun. Just look out tomorrow at night and you'll see that black stuff that's behind the moon. That's the background. That's called space. That's nothing. That's got no shape. You can't draw a picture of space. In fact, you said it's nothing, but you didn't tell me what nothing is. You got to say what nothing is. You got to define the word nothing. It's easy to say it's nothing. Well, what do you mean by nothing? See, nobody has defined the word nothing in 10,000 years. Okay? Okay, my car is square. Is it a drawing, or can we go to the store in your car? Okay, so again, we have several issues. People get these confused, and it's important to highlight these to show where the error is in this reasoning, where the error is here. Okay, so let's go with the first one. There's several errors here, and let's go with the first one. And it's this one. Here we have his car. Okay. My car is a square. That's the object. He's talking about an object. Square is an object. It has shape, as I showed a second ago. Okay. Is it a drawing, or can we go to the store in your car? Now he's talking about something else. He's talking about whether the car exists. That's a different issue. Totally different issue. Okay. So on the one hand, he's confusing the word object with the word exists. And that has a long history. Everybody, Aristotle, David Hume, Kant, Ayn Rand, everybody confused object with exist because they kept putting more words in there than they needed. Here's the idea of Hume and the idea of Kant. They both said, in fact, Hume said, the idea of existence then is the very same with the idea of what we conceive to be existent. To reflect on anything simply and to reflect on it as existent are nothing different from each other. That idea, when conjoined with the idea of any object, makes no addition to it. Okay, so whatever we conceive to be existent. Wrong, Mr. Hume. Not true. And then David Hume, let me put this guy over here and bring this one down. Give me a second here. Okay. And Immanuel Kant, he said, by whatever and however many predicates I may think of a thing, even in completely determining it, nothing is really added to it if we add that the thing exists. Both these two gentlemen, they were so-called philosophers. They were trying to do ontology, and they failed miserably, just like everybody else. Wittgenstein, Russell, Ayn Rand, everybody that came after made the same errors. They never were able to define the word object and the word exist. Those are the two key words. They don't belong to philosophy. They don't belong to ontology. They don't belong to Aristotle or Plato. They belong to physics, strictly to physics. Physics is the science of objects. Physics is the science of existence. You must define the word object. You must define the word exist. You got to tell the crowd what a thing is and whether it exists or not. You should be able to, that's as a minimum as a physicist. That's kindergarten physics. These two fellows were not able to distinguish between object and exist, and that's the same error this other fellow made. He confuses object with exist. He thinks that because a car is square, or whatever, he says, I got a square. And then I said, I can't touch a square. I can't move a square. I can't do anything with a square. Because now you're talking about whether the square exists. That's a totally different issue. First, you got to define what an object is. You got to define the word object. And the other issue is, you can't just say, well, I don't like your definition, Bill. I don't like your object definition because it destroys my religion. I don't care. Physics is about proposing, not about criticizing. Criticize me all you want. You don't like my definition, fine, love it. Tell me what it is. We are 8 billion people in this conference room, and the doors are locked. Nobody can get out until we define the word object. So don't tell me what an object ain't. Tell me what an object is. You got to tell the crowd how to define the word object. That's where you should begin. You should not begin with the criticism. You should begin, this is my definition of object, and this is why your definition, Bill, is wrong, incorrect, irrational, whatever you want to say next. That's the way it works, okay? And see if I can get another issue in there. Yeah, well, no, Here, just define the word exist. I do define it, that which has shape. That's what object is. And then an object that has location, that's what exists. Okay, so we do have a rational definition that we can use consistently. And of course, this destroys a lot of religions out there. The space-time exists. Does a black hole exist? Is it an object or a concept? Does dark matter exist? Is it an object or a concept? So these are the issues that need to be addressed, because people bring in all these saints and gods and spirits and souls and energy and mass and force and time, and they say, well, these are objects and they exist. But not in science. Maybe in ordinary speech and mathematics, maybe over there they exist. Not in science. Science, you have to define the word object, define the word exist. You can't do physics without them. And once you have those, well, all these words, you can't use them to say, well, I transferred energy. What did you transfer? What did I get? You threw energy, you transferred it to my hand. I didn't receive anything. I want to know what I received. Please illustrate what I received, because that way I can see it. I can see this energy thingy. Okay? And yeah, they use all these euphemisms, and that's what they transfer, and that's what they bend and what they warp and whatever. Okay, and yeah, at this point I had one of my dear friends, we had him here in Frankfurt, we had him in Buenos Aires as well, and let's see if I can get him in here. And when he was here in Frankfurt, I beat him up very bad. He came with another fellow, and I really beat him up badly, okay? They thought they were going to push me around. And this is how I left them, I had these two broomsticks, and I didn't use my baseball bat or my dough roller. Look how I left them. I just knocked them out. And so they learned to respect me after that, They said, oh, Jesus, But even though I beat the crap out of them, apparently at least one of them still doesn't understand. And so I guess I'm going to have to use my dough roller next time to learn him, I got to learn him. Okay, so let's find out. He says the following. Again, with respect to the word object, it troubles him quite a bit. And so, yeah, we need to get to the bottom of this, find out. He says, imaginations of objects have shape. Why not smell too? Okay, I can smell. I can imagine smell, he says. A unicorn has smell. Bring a unicorn to the conference. It has smell in every way. It has shape. In your imagination. The answer is no. No, and why not? Okay, let's find out why not. Okay. Here it is, okay? Here we have this word, imagination. And what does it mean? Imagine, to form a mental image of. And something not actually present to the senses, okay? But which sense? Well, it's forming a mental images or concepts that are, of what is not actually present to the senses. But what is an image? A physical likeness or representation of a person, animal, or a thing, photographed, painted, sculptured, or otherwise made visible. You got to make it visible. You can't make smell visible, and you can't make taste visible. Okay, you can't make these things or hearing. You can't make those visible. Visibility is circumscribed to imagination, to images. Okay, so no, when you say that you can imagine smell, you're using ordinary speech. Actually, you got to be more careful with the language when you're using it for the purposes of physics. I can draw a square for the ET. Okay, so we have an ET, and we're trying to teach him our language, and I can draw a square right there, in front of him. But I can't say, well, it smells like a skunk. And he says, what's a skunk? Or what does a skunk smell like? Well, I can't reproduce it. What am I going to do? I can't make an image of smell. I can't make an image of taste. It tastes like salt. He never tasted salt. They don't have salt on his planet. So what does salt taste like? Unless you have the experience, you don't know what the guy's talking about. But square, I don't need for him to have any preconceived notions. I can just draw a square and say, look, this is a square. And I name a square and point to it and say, that shape, for the rest of my talk, I'm going to call it square. Okay? Okay. One more here on all these were on object. Okay, what an object is. Lots of issues there, and yeah, that's got to be settled. Okay, the drawing on paper is a drawing. In other words, if you draw like a square, okay. And so I just want to clarify here one thing, and here it is. Okay, I can draw a circle. Okay, I'm going to draw a circle here. Okay. The drawing of the circle is not an object. Drawing is a verb. Okay, so hopefully we have a finished product. And here you have a circle. Is that a circle? No, I'm still drawing. I'm still in the process of drawing it. Okay, and I never finish it. It's like the incomplete symphony. The the incomplete circle. I have not finished a circle, so that's not a circle. That's not a shape. I have to. A shape has to be all around. Has to be complete. Okay, that's a pattern. I call those patterns. In other words, pattern is not a shape. We're still not complete. We don't have a circle there. Okay, this is a circle. So. Okay, so that's a complete circle. I have to point to it. It's got to be complete. It's got to be finished. I have to have the full statue there. Okay, I can't have half a statue. I can't be drawing it. Okay, so drawing is it's not the verb that's the object. It's the finished product that's the object. That's what I'm trying to say here. Okay, so make sure you don't confuse that. The drawing or half a drawing, I haven't finished, with a final product. I have to have a complete statue before I can call it that's the object. I can't just do half a statue or half a letter. I can't have half a 5, still drawing it and say, well, that's an object. Or the letter C, I got to complete the C and turn it into an O for it to be an object. The letter C, I'm still in the process of drawing the O. And so keep those issues in mind. Okay, another thing brought up by my good friend says, defining shape independently of physicality. I would define shape that exists as having a spatial inside and outside. Okay, I like the fact that he uses the word space, okay, to define an object or shape. I like the term form for shape with existence. Okay, so let's find out what the problem is with that. Okay, here we have it. Here's the problem. Let me put it here to the side. I'll cover my face. What is the problem? The problem is shape is a property. It's an attribute of an object. And so it's a concept. And concepts don't exist. And exist is equal to object plus location. So you cannot talk about existing shapes. Okay? You can talk about existing objects because shape is a property of an object. Object is already defined as having the property of shape, which is the only universal property of all objects. All objects have shape. But if you know of an object that does not have shape, please bring it to the conference or draw it. I want to see what you're referring to, an object that doesn't have shape. Okay. So yeah, the word shape is, the word object is very profound. It took me a long time to figure out how important that word was, and you can see why people are bringing all these issues. You know, it bothers them, or they don't understand it, or they're trying to ask themselves questions, trying to reason it to see if it matches their notion of what object is, if the definition stands its ground, if it really is solid. Okay? And I'm telling you, it is solid. But we'll continue. There were more issues related to shape. This fellow says, I say that the object as such must have 3 spatial dimensions. Well, the problem is that a dimension is one of the properties, and you have 3 dimensions. You have 3. 3 is a concept. Okay, so you need length, width, and height. And so, and you have a comparison because length is not the same thing as width, and width is not the same thing as height. None of these 3 are related to each other. So you can't use the word dimension to define the word object, because the word object must, of necessity, precede the word dimension. Okay, especially, you know, you need to define dimension first, because then you would begin by defining dimension before you define an object. Okay, and again, there are objects. Again, shape is because all you're doing is giving shape. What is the purpose of the dimension? Is to talk about shape. What is the point of the dimension? Okay, and again, what you're saying is that the thing has shape. And we have shapes that are 2-dimensional, shapes that are 3-dimensional. That's all we're saying. So the fact that this is 2 and this is 3, so what? You know, all you're doing is qualifying an extra level or a further level, you know, what an object is, or different types of objects. You're already comparing objects when you're talking about dimensions. Okay, another issue, also related to object. Lots of them. Everyone wanted to say something about I said that it is not enough to define an object as something that has form, shape, something that has spatial form or contour. Although the shadow has form, you know, because a shadow is not a standalone object. Okay, you need shadow is light. That's all it is. It's just a reflection or refraction of light, and so light does not stand alone. Light is, you know, under the rope model, it's just the rope coming out with a certain frequency, a certain length. Okay, that's all it is. Okay, so whenever you talk about shadow, you're talking about light. You're not talking about the object itself. You're talking about what the object is doing. You know, you're talking about red light or yellow light or whatever, different frequencies of the rope. Even under quantum, you know, you're talking about frequency. So anyway, you look at it, you're talking about what the object is doing. Okay, when you talk about shadows, it said, you said that shadow is not an object because it is not a standalone independent. Yeah, you got to understand that. And so your definition of object shall be updated. Whoa, wants to amend my definition. Object is what has shape, and it's standalone and independent. And again, it shows that what people never learn, and people never learn to define words scientifically. Let me tell you what the problem is. The first problem. The more words you put in a definition, the more the naysayers, the skeptics, the devil's advocates are going to come in and batter you. It's the other way around. You got to make your definitions very concise. More concise, the better. If you make them concise, it's harder to attack it. Okay, that's the first issue you got to understand about definitions. People think defining is just, oh yeah, definitions. No one has been able to define words scientifically in the last 10,000 years. Okay, we had to come in with rational science to define words because nobody did. Okay, and yeah, when you define words, people say, hey, that destroys my religion. I don't like that definition. Okay, tear it down. And don't just tear it down. Tearing down is the easy part. Show us what you propose in exchange. That's where you have to use your brain. And so don't tell me what it ain't, tell me what it is. And here he's saying standalone and independent. We don't need those two words because, again, if I show a halo, what is a halo? Halo of an angel, right? The one he carries, the little disc or ring he carries over his head. I show you a ring and say that's a halo. And you say, no, that's a ring. You say, what do you mean a halo? Yeah, I need the angel for that to be a halo. Otherwise, it's a ring or a plate. With the angel, it has this holiness, which is what's embodied in the word halo. In the halo of the angel. In other words, you have to have the angel. In that sense, it's not a standalone object. Okay. Likewise, the magnetic field, you need the magnet. If you don't bring the magnet, you can't just bring the magnetic field. In that sense, it's a dependent object. It's not a standalone object. Aside from the fact that a field is something in motion. There's something in motion inside that body called field, magnetic field. So it's not a standalone object in that sense. You don't need the word standalone because when you're talking about an object, you're talking about one thing. If you put standalone, then you're immediately suggesting that there's some other object. So if you put standalone, if you qualify that specifically, people will say, what did you mean by standalone? What did you mean by independent? And then you get another can of worms. No, that which has shape. We understand that. You point to it. I could say it's that which you can point to also. What do you mean by point? Are you talking about the mathematical point? They're going to just drown you. This has to be simple. And let me tell you what the issue is, what the bottom line is for the word object, okay? This goes for everyone out there who's got a question, okay? This is the only issue you got to deal with. This is where the context is, okay? Let me get it up here. You got to tell me which of these criteria you're going to choose as a definition for the word object. Today, everybody and their mother out there has the first two, see and touch. That's the default that people use. They think that an object is that which you can see and touch. That's why they relate it to 3D. That's why they relate it to exist. Because they say, well, an object is what I can touch, what I can see. A table is an object. Well, you can't touch the table I have in my head, the one I'm thinking of. And you can't see it either until I draw it maybe for you. And no, you can't smell it. And you can't hear it or taste it, okay? Not the one I have in my head, okay? Just, you got to clarify these things for some people. Okay, see, touch is the criteria that you're using today. That's the one we want to destroy. No. An object is not that which you can see and touch, because that allows the mathematician to go into the lab and say, well, I want to see and touch gravity. I want to see and touch light. I want to see and touch the magnetic field. And so they go to the lab, they want to do experiments to elucidate the nature of these invisible, intangible entities. And what's their conclusion? There's no object there, because I can't see it or touch it. No, there is an object there, because that's not the definition of the word object. The definition is the word shape. Okay? And yes, it is a standalone object because you don't need to qualify it as standalone. All you have to do is say, well, there's a single object in there. That one that I'm pointing to. Shape is all I have in front. That's the only property that all objects in the universe have. In fact, if you put all the objects in the universe, none of them are standalone. So I have to treat it as a standalone object for the purposes of defining the word object. Okay? And none of those, volume, motion, made of, mereology, what is it made out of? How many atoms is it made out of? We don't care about that. That's not an object, because if it's made out of things, then it's not the only object in the universe. Then you have all these objects that make up an object. You're not talking about the elephant. You're talking about the atoms that make up the elephant. That's why mereology is not a part of science. It's part of religion. This, what is it made out of? And a lot of people have this notion of what an object is. Again, see, touch, and what it's made out of. That's deeply ingrained in the minds of people. It's very hard to get them out of there. And no, this is much more simpler. You remove all those criteria. The one you stay with is shape. It's the only universal property of all objects. All of them have that. And no, an object is not the subject of a sentence. It's not just a noun, except if you want to turn that around and say, well, for the purposes of physics, only objects can serve as nouns. Okay? It's not the orbit of Jupiter, it's Jupiter orbits. Orbits is the verb. You can't say orbit is a noun, orbit is the subject of the sentence, therefore it's an object, which is what Russell and all these Wittgenstein, all these philosophers had in the back of their minds, that, if you can talk about it, well, then it's an object. Not in physics. We can talk about the word orbit or the word motion. Those are not objects for the purposes of physics. They are not nouns. They are not subject matter. The subject is the actor, the agent. And in the case of gravity and all those, it's secret agents, Mother Nature's secret agent. Color is a verb. Color is a verb. It's not a noun. Okay, not in physics. Color is a frequency of light. That's all it is. Okay, exists, that comes later. First we need the object, then we'll figure out if the object exists. Superman doesn't exist, Snow White doesn't exist, square doesn't exist, dry-bar doesn't exist. Why? Because, primarily because they're two-dimensional in this case. The other ones are, imaginary. I can imagine them, I can draw them, but they don't exist. Why? Because they don't have location. They lack location. 3D, same thing. You have 2D objects. And form is a synonym of the word shape. Okay? No difference in physics. Only in religion is form equal to shape. Okay? In ordinary speech, where they never clarify these concepts, the fine details of these concepts. No, in physics, shape and form are perfect, exact, 100% synonyms. Okay? No difference between those two words. Okay? Okay, another issue here. The rope is a closed loop, so technically it's a one object universe without relative location. So it doesn't exist? Yeah, it doesn't exist. You can't say in physics. Not in ordinary speech. See, people you bring this notion of ordinary speech. What do you mean love doesn't exist? Yeah, in physics you can't say that love exists. That's in ordinary speech and mathematics and all these other religions. They say love exists. Grace exists. The spirit of my soul exists. Now you can't say that in physics. In physics, it's literal. If it exists, it's because it's got location. God wants to exist, very simple. He's got to first be an object. He can't be a concept like love or grace or the spirit. And second, he's got to have locations. There's got to be a distance between God's chest and mine. Then he exists, by definition, not because I believe or disbelieve. Okay? But then the question is on the rope. Yeah, and here it is, illustrated. Okay, cover my face. Okay, so here it is. That's exist. Okay, object plus location. The rope exists. Okay, what this fellow was talking about probably was the thread. If we unravel the ropes and the atoms, we have a single thread in the entire universe, which is what you see down at the bottom. That thread is what is going to twist around and form all the atoms and the ropes that interconnect them in the universe. There's a single thread in all of space. That's all that there is. And so the question, does the thread, because you can say that the atoms exist. Those two atoms, one two-dimensional, the other one three-dimensional, just for illustration purposes, they exist. Why? Because there's a distance between them. They have distance with respect to all other atoms in the universe. So we say they exist. Why? Because they're objects, and we treat them as if they were chopped off at the rope. And we build things with them because we can't see anything between them. We don't see the ropes, so we treat them as independent objects. And so we say, yeah, the table exists, the chair exists, because they're separate objects. Okay? Is the thread, can we do that with the thread? Well, the thread, would need another object for the thread to exist, to say that the thread exists, to apply the word exist to the word, to the single thread in the universe. Well, if there's another parallel thread out there, yes, we could do that. If there is another universe out there, we could do that. If there's another thread that turned into all these atoms in a parallel universe, so we have two universes. Now we can talk about universes in that sense. We would have a single space because space has no boundaries. But we would have two groups of matter, two systems of matter, and they're not interconnected. Okay, so it's like two galaxies. Except galaxies, Andromeda is connected to us through the electromagnetic ropes because all ropes are interconnected. Okay, and why do I know this? Well, because we're pulling on Andromeda for one, and second, we can see Andromeda. The only reason we can see Andromeda is that we're peering through the gazillions of ropes that interconnect every atom in Andromeda with every atom in the Milky Way. That's why we can see Andromeda. If there were no ropes, there would not be a medium through which the torsions propagate, and we would not see Andromeda. And that's what I'm referring to here in two parallel universes. We're saying that none of the ropes in our universe are attached to any of the atoms in this parallel universe. So we could have two universes all interconnected within each system, but not connected between the two systems. Okay? So we have intra, but not inter. Okay? So what happens in that case? Well, something strange, because in that case we could say our universe exists. Our bunch of matter exists. And in that case, the thread can be said to exist, but only under that condition. If there is no other universe, if this bunch of matter is the only system of matter that exists, interconnected in the universe, then that's it. You can't say that the thread, if we unravel all the atoms and all the ropes and just come up with our famous single thread, that thread cannot be said to exist. Okay? So the only way maybe you can say that a piece of the thread, the one on that side of the universe, is opposite of this piece of the thread. Okay? That's the only way you can do it. And that's more or less like chopping the atom off at the rope. The rope forks into the atom. You assume that you cut it off there because we deal with our matter every day, like tables and chairs, and we do not trip or get tangled with the ropes that interconnect all these objects. Why? Because an object is not that which you can see or touch or trip over or get tangled with. An object is that which has shape. And that's what the rope is. The rope has shape, but it doesn't have the property of see and touch. And it's very hard to get that through people. People will say, what are you saying, Bill? Because that's our experience. Our everyday experience is see, touch. That's why we extrapolate that property or those attributes to the rope, and then that's when people say, well, I don't understand it. How can I understand something I can't see or touch? Well, the only way is to imagine how Mother Nature uses the rope to do her daily things, light, gravity, magnetism, so on. Okay, another issue. That's his definition of concept, describes a relation between concepts or nested concepts. And the only thing I want to point out here, we have to be very careful with the definitions. Don't put words in, don't take words out. I mean, if you're just going very briefly over it, that's okay, informally. But formally, I want to make sure we understand the definition of the word concept, okay? And I don't want anyone taking a single word out or putting a single word into that definition. It's got to be perfect. It's got to be exact, okay? So here it is. What is an object? That which has shape. Don't add, don't subtract. Concept. What is a concept? A word that invokes or embodies two objects, and you can put it as a synonym as a relation. Yeah, it is a relation, but the key word, the key definition, a word that invokes or embodies two objects. First, you need to define the word object. When you have two of them, you have a concept. Okay, so that's the way it works. Just want to clarify that. Don't be loose on the definitions, because people are going to murder you. The devil's advocates, they're going to say, oh, what about this and? You put the word and in there. What do you mean by and? Oh man, they'll chop you to pieces because their religion is at stake. People are fanatic about these things, okay? So that's what I've learned in the last 20 or so years. You know, people defend their religion with all their might, and so you can't say, well, my definition destroys your religion, because that's what you're doing. And so one thing is, first, they can criticize all they want, but they have to propose something in exchange. You can't leave the room until someone's got a definition. One of you two guys has to beat the other guy. You can't both be winners. One is the champ, the other guy's on the floor, knocked out, okay? And he can leave, you know, knocked out, but he's got to get his definition in there. And again, there's no arbiter, no referee. Everybody continues to believe whatever they want to believe. Nothing changes there. It's just to try to make sense of this universe that we're interested in. Okay. Okay. Bill says you can't have adjectives with true signs. Then in the next breath, he calls it electromagnetic ropes. Shaking my head. Well, the issue there is that I use EM, electromagnetic, as an adjective for the rope, only first for convention, because, you know, they had the electric and magnetic field. I'm saying it's not field, it's thread. It's a physical object. Field is a concept, an abstract concept, mathematical concept. And so there is no such thing as an electric field that I can bring to the conference room. There is no magnetic field I can bring to the conference. Okay, you can bring a thread. You know, here one of these is the electric thread, the other one is the magnetic thread, and I'm talking about threads, so you understand what I'm saying. So the only reason I use the adjective, I mean, I can just say rope. I don't need the adjective. The reason I use the adjective, one is to relate it to light, the other one is to keep with convention. And it's just for the sake of conversation, nothing more than that. The object is the rope. Electromagnetic is not part of the object called rope. Okay. In fact, again, you have two threads making up a rope. We just call that object chopped off right before the atom. We call that thing a rope, because that's what it is. You treat it as if it's made out of a single piece, even though it's made out of two pieces. Okay. So keep that in mind. The thread is the real object, not the rope in that sense. But we have to treat the rope as an object, because that's what we're going to be using to simulate light, to simulate gravity, and so on. So you got to put it in the proper context. That's why we use EM. Okay? But again, not necessary. You can just say rope. Okay, and final one I want to relate to this fellow. Okay, lots of comments on this came in. I'm not going to address them all. And this is Mr. Ken Wheeler. And Mr. Wheeler, someone told me that he put out definitions. I don't know if he put them on in response to my criticism of his theory, his arguments. Okay, and I've got a couple videos on that in the past. You can look them up. Ken Wheeler, 1 and 2, I think. Maybe there was a third one. I don't remember now. And so he came up with a list of definitions. And so I went in there and looked at some of these definitions to find out if anything changed since the last time that I analyzed them. And so I went and looked at his definitions. And I looked at essentially 3 or 4 of them, you know, a couple of them here. And here's the first one, ether. He vouches for the ether. And again, that's why I like to destroy the ether. Any person who comes near me, they better not mention the word ether, or I will treat them with the respect that they deserve. Okay? No ether, not in science. It's only in religion that they use the word ether. Okay? What does he mean by ether? Ether is pure potential. What is potential? Well, it's a concept. That's what potential is. It's a promise. That's there is no physical object called potential, but he thinks he answered the question. Oh, ether is potential. Non-Cartesian counterspatial inertia. Inertia is a concept, counterspatial for sure, you know. I'll get that into a second. Counterspace is, where I put my beer. And they can move my beer and they can move the counter. But when they start moving the counter space, I know that's time to go home and I need a designated driver, you know. Ether we loosely call energy. What is energy? Nothing. It's a concept, okay? All matter and atoms are compounded ether condensate. How can it be a condensate if it's a concept? How do you condense a concept? What do? You take love and you condense it and make it, a heart with it? I don't know. What are you condensing? So he starts defining it as a concept, then he starts manipulating. He starts molding it like silly putty. Okay, he treats it like silly putty. Pure potential again, which things are possible. All matter and atoms are compounded ether. So if it's an atom, how it can be compounded ether condensates? You see how he crosses the line. He doesn't even notice that. Okay. Light is a longitudinal disturbance in the ether. Quotes Tesla. Again, Tesla was another fellow had no clue whatsoever about science. Inventor, yeah, he had a knack for going into the lab and looking at things and saying, oh, look, this can be done that way and this other way. He was smart in that sense. Okay, he was lab smart. Okay? He worked for Edison first, then he went working for Westinghouse. But Tesla, near the end of his days, he said, someday, he said this, okay? He said, someday, he said this to a reporter, someday we'll discover what electricity is. Meaning he had no clue what electricity was, and this was at the end of his days, okay, just before he died. Okay, that's one definition. Here's another definition, just going to look at a couple, just so you can see that Wheeler has no clue whatsoever about anything. Counterspace. See ether. Go see ether. We just came from there, okay? Also accurately called the ether realm. 0-point energy. Which is energy? Nothing, okay? Realm or simply the ether. The realm or pure potential. So he's just putting words in there that are meaningless words, okay? You can go on forever with all this. And then he talks about 2 dimensions and dimension, 9-dimensional. He never defines the word dimension. It's more like dementia more than dimension. Okay, but then we get the punchline, and here's that one. And it's the word energy. What is energy? Because he defines energy now that he's defined ether as energy, counterspace is energy. What is energy? Okay, energy is the ether. No branch of science has explained what energy is. Okay, they have no idea. Nobody on Earth can accurately define the term energy to any person's satisfaction, including Mr. Wheeler. Okay? It is far more simple for humanity to replace the word energy with the word field. Okay, what is a field? A field is an ether perturbation modality. Ultimately, there is only one field, that being the ether itself. So it's just a bunch of words. He says X is B. Okay, what is B? B is C. Okay, what is C? C is D, and D is X, or A, whatever I said first. Okay, all which is, that being the terms field and energy. All which is, that being the terms field and energy. Everything is field and energy, and what is field and energy? Nothing. It's a concept. These are concepts. What is field? A bunch of numbers. That's what field is. So he hasn't, if it's a something, draw it. Give me a picture. And if it's a concept, don't tell me that it makes up everything, that makes up all atoms, that it's everything out there, because all you're saying is God. You're saying God is everywhere, God is everything. You haven't told me what God is. Magnetism, in short, is energy as manifest. Whoa, as energy as manifest. Whereas the ether is energy in potential, and the dielectric is energy in torsion. So we have energy, we have this concept that's moving around, being torqued, in which he tells us, oh, don't use the word energy, use the word field. And what is a field? It's the ether. What is the ether? It's the energy, and you keep going around in circles. And So yeah, really, after looking at him, at his definitions, the first time I criticized his book, today I'm criticizing his definitions. I get a different notion now of Mr. Wheeler. I think this person suffers from some mental problems. I really do. Not because I want to insult him. I really think he's got a mental problem. First, he's an angry person, very angry person. He's angry against the establishment. I don't blame him for that. And a lot of his followers are angry at the establishment. That's why they follow him, because he cusses them out and they like that, and they say, oh yeah, we need someone like him. He's an angry person, but that's not the issue. The issue here is when you look at first his book, which I've covered that in the past. I don't remember the name, something about magnetism, and the definitions that I just scanned, because I didn't read all of them. I read a lot of them, and made no sense whatsoever. I get the impression he's got a very scrambled brain. I mean, if he really believes this stuff, it goes beyond rationality. I think he's got some mental problem. And in that sense, I don't like to beat up on Down's patients. He's really got a problem. He's got to take care of. I don't know if he's aware of that or not, but he's suffering with some acute problem there. Okay, with that, I'll see you on Wednesday. We'll continue with some quantum mechanics. We'll see you then. Bye-bye.